That look right? And let's click on what solution looks like. Okay, gotcha. Okay. What we're dealing with here is a shape that's basically a part of a circle. So if I do y equals 1 minus x squared, do you know that's another version of x squared plus y squared equals 1? You know, if you rearrange that, you get this. And so that would typically be a circle radius 1. If you rearrange this one, you've got an x squared plus y squared equals 9, which is basically another circle, which looks like that, but its radius is 3. And then I believe it went and said something about the x-axis, didn't it? So I'm assuming that it said something like above the x-axis. So the shape that we're dealing with, this fill in here, our region D, is essentially the top half of a donut. So that's what I'm assuming the directions were. Can you remember what the function was that we're going to do this for? Was it 7z? Anyone remember?
It's 1 over the square root of x squared plus y squared.
Okay, that's cool. That's actually going to convert as well. What else?
Is that right for the density being inversely proportional to the distance from the origin?
It is, and exactly that's what that is. So x squared plus y squared with the square root, that's the distance. And 1 over that is the inverse to the distance. Okay, so we are going to be finding, to start off with, this fella, which is 1 over the square root of x squared plus y squared dx dy. Let's change that to general dA, and we'll call this a region D. Right, when I look at a half circle like this and I look at an x squared plus y squared, my brain immediately thinks, let's do this in polar. Now, won't this become 1 over r?
Yeah.
Right. And you always have an r with polar, so they're going to cancel out without any issues at all. If I want to describe this region, wouldn't you go 0 to pi and 1 to 3? So this would be r equals 1 to r equals 3, and theta equals 0 to theta equals pi. Right. Now, do we have was there a density function in this, or was that what the 1 over r was representing?
That's a 1 over r.
Right. So basically, this question is a very simple integral, doesn't it? Because those cancel out, and you're just basically doing a double integral of 1 between here and here. So I'm guessing the answer to that would be 2 pi, unless there's something else I missed.
Thank you.
Right. Was it setting up the thing, or to realize that it's polar?
Yeah, I was setting up the semicircles, kind of threw me.
And the 1 over, what did they phrase it as? Inversely proportional to the distance to the origin? That was a very weird way of saying this fella.
Thank you.
Okay. So let's move on, and I'm going to see if I can do some work on the last section. That's not the one I want. Here we go. So you should be, in a few moments from now, looking at some examples that I put together. That way I can just talk through them. think it's this one. Right, triple integrals. They have the same kind of feature as a double integral, but you do it to 3 variables, typically x, y, and z. And the x, the y, and the z can be in any order that you like. And the first type of question is pretty standard. The limits of integration are already given to you. Have you noticed that the final one, because we always do these things inside to the out, the final one must have numbers in it or else the question doesn't make sense. Also, since this is 0 to 1, the second one is this guy here, and that's the x variable. So this should be saying, I've got it over here, x equals y to 2y. And the inside one is using z, so that's z equals 0 to z equals x plus y. The typical way that they write the question is this. I find it much better to write it that way because it's clearer in my brain who the y values are, who the x's are going to get replaced by, and finally who the z's are going to get replaced by. Now, you do what you did in the double integral, but you do it 3 times. So the first thing you're going to deal with is the z's. So you've got 12xy, right? You pull that fella out and you integrate it with respect to z. Well, 12xy is just a constant, so you're going to get 12xyz. And then you plug in the limit z equals x plus y, z equals 0, which takes you through a few steps, and eventually you get to here. Now, the nice thing about that particular triple integral and quite a few of the others is, once you get to here, isn't it really just a double integral question? Right? You just do what you do with double integrals. So we're now going to integrate with respect to x, which hopefully gets you this fella. You're going to replace the x with 2y and the x with y. So here it is the 2y, take away, here it is with a y. Actually comes out, it's a really nice answer. You then integrate with respect to y, plug in 1, plug in 0, and you're done. So if you get, and there is quite a few examples where the integral is pretty much given to you. This is your process. Now, the one I've got here is the nicest version of that, because everything is just basically the power rule. You know you're going to get ones occasionally from time to time where you might have to do an integration by parts or maybe a u-sub, and that is possible. And if it is, you just be careful and you should be fine. Now, the second one I've got an example of here is a triple integral where they describe the region. And in this case, they describe it using this information. And when you look at a question that's like this particular one, what you got to say is, okay, what have you told me? I can do it in any order I like. I can go x first or y first or z first. And first thing that strikes me about this one here is these two guys here. Z equals x squared minus 1 and z equals 1 minus x squared. That kind of tells me that that's the first guy to do. Do you see how the z's go from here to here? dz. So I'm going to do z's first. Now, if I draw a sketch using these two and look at it from x and z, it's a bit like getting the 3D shape and just looking at it side on. You see that you've got the two curves going up and down, and you see that the region you're talking about is this little bit in the middle, and the x's go from -1 to 1. So that tells me to use -1 to 1, and x's is my second fella. Are we good with that? Now, if I then go to the last fella, do you see how they finish the information with y equals 0 and y equals 4? If they tell me y equals 0 and 4, do you notice I made that my last one? Because that uses numbers, and that's my y. So, based on what they give you, you have to decide who's first, in this case z, who's second, in this case x, and who's going to be last, this guy y. But once you've set this up, it's just like question 1. You go through the integral and you do the z's first, then you do it with the x's next, and then finally you do it until you're finished, and the final answer ends up being, in this case, negative 64/3. Is there any issues, anything that you're not sure about in this case? We cool with that? If I don't hear anything, I'm going to go and look at some of their questions from the text from WebAssign.
Yeah, that seems straightforward.
Okay, so let's just look at, the various versions that they have, because when you do anything in this textbook, there's lots of little tricks that they bring in. So here's a triple integral, right? So I should be able to do a share on that. Okay, are you looking at 15.6 now?
That's what I.
Yeah.
Okay, that's good. So let's put the answers away. They're very distracting. Right, let's look at the examples. There are 13 questions here. The first question, isn't that a standard triple integral, just like example 1? Right? Now, in this case here, the first integral is with respect to z. So you're going to integrate 18xy with respect to z, and you're going to plug in z equals 0, and then z equals x plus y, and then so on for the others. Question 2 is very similar. Do you see in this case, you're going to integrate first with respect to y. So this means y equals log x to y equals 0. This means x equals 4z to x equals 0. And it finishes with z equals 2 to z equals 3. Are we cool with that one?
Yeah.
Right. 3's, same kind of deal. That one there is in a carbon copy of the example I just did. Right, it's this one here. Now let's look at the setup for this one. We're going to do a triple integral over some region E, and the function itself isn't that interesting. It's just 7z dv, and it's a volume. And we have a cylinder called x squared plus z squared equals 9. And we have some planes going on. We have an x equals 0, a y equals 3x, and a z equals 0. So what we're trying to imagine here is, oops, let's switch over now. Right, what we're trying to imagine here is how to recreate this fella as a triple integral. So far, so good. Now let's see what I have here. I have a z equals 0, and I've got this guy. I've got an x equals 0, and I've got a y equals 3x. So if I'm trying to just put some of this information in a visual format, that's basically all those things are telling me. The z equals 0 and the y squared plus z squared equals 9 is kind of interesting, because when I look at those guys, when I look at those guys, what I'm seeing is, oh, quadratics. So I'm thinking maybe some of these guys would be better fitted or better suited to being polar. So if I take y squared plus z squared equals 9, and I match it with z equals 0, what you are going to generate here is a circle, radius 3, right, going from the center to the outside. Now, what that allows me to do is, can I now do the y's and the z's in terms of polar coordinates? And not only can I do that, can I do it in terms of polar coordinates that have numbers in them? So, for instance, it will be theta equals 0 to theta equals 2 pi, and it will be r equals 0 to r equals 3. And then it's going to have an r dr d theta. I've used up 2 of the 3 triple variables. I've used up the y's and the z's, which means that this fella here is the x's, which means that I'm going to do the x's first. And right now I'm just going to call that guy 7z. Now, what do I know about the x's? Well, the x's go from 0 and they finish at a third y. You see how I rearranged that guy? X equals 0 to x equals a third y. So I've now set up what the triple integral looks like. These two take care of the y and z's, and they do it by using polar. This fella is the x's from 0 to a third z. I knew it had to be the x's because the polar used up the y and z's and they're done, right? Some uses up the y's, right? Some uses up the z's, something uses up the x's, right? So I got all of them there. Now, I got a little bit of tweaking to do, but not really much. 0 to 2 pi for this fella, 0 to 3 for this fella, 0 to 1/3 y. 7z becomes 7 times. And how am I going to write z in polar coordinates? I'm going to call it 3 times the cosine of theta.
Could you have called that 3 sine
Sine
of theta?
Actually, yes. In fact, z is going up the way, so z is equivalent to the y, so I should have used that. In my little picture, y, z, yeah? Agreed. Now, at this point here, we are pretty much done. So I'm looking at this and I'm trying to see, is there a way I can make my life easier? Well, that 3 and the 7 gets me 21. That's a sine theta and that's an r. So why don't I do 0 to 2 pi of 21 sine theta d theta. R equals 0 to r equals 3 of r dr. And the guy that I missed out here is the dx guy. And now I can do the integral. Oh, okay, can I do that? Okay, that back. If that third one had been numbers, I could have done what I just did. But it's got a y in it, so I'm stuck with that. Do you know when I end up plugging in the y to this answer, won't I have to replace a y by an r cosine theta? So when I do this fella into this fella, anything that's y will become an r cosine theta. Do you want me to take you through that question to the next step just to show you what it is? Because I kind of screwed up here. Would you like to see the next step? Okay.
I was actually wondering if the z being sine, is that arbitrary and you would just call y cosine?
Yeah.
Okay.
If I switched it round, if I orientated it differently, the sine would become a cosine and the cosine would become a sine, but the final answer would end up being the same. But I think orientation-wise, we tend to think of x and y as horizontal and z as always being vertical. And if it's a choice between an x and a y, x will be horizontal and y will be vertical. Now, I'm going to rewrite that guy that we had a few seconds ago. It's the integral from 0 to 2 pi, followed by the integral from 0 to 3, followed by the integral of x equals 0 to x equals 1/3 y. And the guy that we had, which was 7 times 3 lots of the sine of theta. And then we're going to do a dnx, an r, a dr, and d theta. I'm just rewriting that guy nicely. Okay, let's see what we've got here. Do you know that 21? I could just stick it out here. And that way I don't need to worry about it being all over the place. And just focus on doing this fella with respect to x. So what would we get? We get sine theta times an x, evaluated at 0 and evaluated at 1/3 y. And then we'd be doing that guy. Now you plug in this fella for x and you get 1/3 y sine theta. Take away nothing essentially. So that's the end of that. R, dr, d theta. The y is now going to become 3 times the cosine of theta times the sine theta with an r, a dr, and a d theta. And those cancel out. Okay, we got that guy. Going a little bit quicker, if you see any mistakes, this is the time to mention it to me. Now, I could have done a little bit of adaptation here. Do you see that x equals 1/3 y thing? Do you know I could already say I know what y is 3 times cosine of theta, and that would have been x equals cosine theta, and that would have been a little bit cleaner in my working. But it ended up happening at the end, so it didn't matter too much. Right, I have to figure out how to integrate this guy, but first we do ours. So it's 1/2 r squared sine theta cosine theta evaluated at 0, finishing at 3. So that gets me 1/2 9. So I'm looking at this fella. I'm almost done. Right, I'm ready for the numbers, right? 9/2 is not pretty. I could pull it out and stick it next to that 21 and that would just get it out of the way for a while. So let's pretend that I had done that. What would sine theta cosine theta, how would you find the integral of that? There are actually 2 ways to do it, 2 that I can think of.
Will u sub?
Yeah, and if you did a u sub, you could pick sine theta and it'd work with the other one. You could pick cosine theta and it'd work with the first one. Or you could use a trig identity. Do you recognize that as a half of the sine of 2 theta? Don't know, slightly easier, but not much, right? And so I'm going to dot that one because I'm running short of paper and I won't have time to do one last question if we can. But just that whole process, did you see how many lines are working and how much intricacy there was in the thing, right? There's a lot of little things you had to fix. And just starting the thing up would be an issue. Now, can you imagine a question like that is in the test, and there's no reason why something like that might not be in the test, then it's going to take you a fair chunk of time. And if the final, I'm making this up because I don't know the answer to this, but let's suppose that the final answer ends up being 21/17, just for argument's sake. when you go to the test, you only type in the answer, right? And then it says wrong. Because it wasn't 21/17, it was 59/33. Can you see that you could have done 90% of the question correctly and a half disappeared somewhere, or you multiplied something slightly wrong, or whatever it is, a little fiddly thing, but nothing major, will change the answer. And so what I'm saying here is working is going to be crucial for these long convoluted questions, because you don't want to lose 5, 10 points, actually most of them are 10 points, 10 points on just having a wrong answer and not showing me any working that goes with it. So bear that in mind, that the working is going to be crucial to make sure that you get a grade that fairly reflects what you did. Now, I guess if you're really, really good and every answer is perfect, then the working's not going to do anything because you're still going to get 100%. But I don't think many of us, apart from me, is perfect. You didn't get that, did you? That one slid right under the radar. That one did. I'll say it again in case you didn't catch it. You know, I used to be conceited, but now I'm perfect.
That's fair.
Okay, you got it now. Good, the sense of humor of some of you is. I miss teaching, because if I was in class right now, I'd be having so much fun just looking at some of your grimaces, but now I only get to see that at a distance, and it's just not the same thing. Okay, we got time for one last question or a concept or whatever it might be. I've got a little thing I want to show you, if you don't. Okay. Do you know those horribly long questions where you get the center of gravity, the center of mass, whatever name they give it, and you've done it with a 2D thing? Do you know you can do it with a 3D thing? Right. So a triple integral can also have a center of mass, and you know the formula for it is basically the triple integral over the region of x times whatever the density function is. You know that guy. Let's just call it dv. Triple integral over the y fella, and the triple integral over the z fella. Right. So it's really just a continuation of what you do in the two-dimensional world, right? And you can always go and look that up to check it out. So what's the little trick of the trade? Symmetry can be your friend here. Right. So if you get a shape, and let's say the shape ends up being a cylinder in 3Ds, right, 3 dimensions. If there is any symmetry in the shape and the density function is symmetric. So a density function that's symmetric would be something like that, right? Or something like that, right? Or something like that, or whatever, right? Symmetric. If it is symmetric, you can get at least one, if not two, of these guys by sheer symmetry. If you look at this shape from above, doesn't it make a circle? And if the shape is symmetric, won't the x and y be the origin? So it means you don't have to fight your way through a whole load of triple integral stuff just to find the x and the y. Now, to get the z, technically speaking, if I knew where there and there is, so if I knew that was 8 and I knew that was 0, and do you know the guy in the middle would be 4? Now, that would be a too easy a question. So what they might give you, and this is more realistic, is you can have a function, a density function, which is semi-symmetric. X squared plus y squared plus z is symmetric in the x and the y, and therefore you can still do this. It's not symmetric in the Z, which means you're just going to have to do Z bar. If you got a question that looked like this, the density function was x squared minus y plus z squared. Right. So you can imagine that function. You should be able to find the x bar and the z bar by just looking at what the picture looks like. Now I've got circles, but can you imagine it's a rectangular box zooming off somewhere, or it's an ellipse, or it's a something shape? As long as you know that the x and the z are symmetric to each other, you should be able to find what the split down the middle is and the split horizontally is and get the x and the z bar. It's just a way of reducing your workload. So always have a look out for, is the density function symmetric? And then look at the shape and see if you can find an x bar or a y bar. It might not be possible to get all three. So can you imagine that the x and the y were symmetric as far as the density function went? But the shape looked like this. You could at least get the x value. It would be 2. You'd still have to do y bar the hard way. You still have to do z bar the hard way. But if it takes you 5 minutes to do each of them, isn't it nice if you can cut back on one of those questions and just cut straight to the chess?
Does that still work if the density is based on the distance from the origin?
Well, the distance from the origin is really cool, because the distance from the origin is symmetric in x, y, and z.
But if the shape wasn't centered on the origin?
If the shape's not centered, you do need to know what the shape is. So let's make it up. Say if the shape is just some random shape with no design to it, the shortcut doesn't work. But sometimes you get lucky. You know, sometimes the shape is made up of something that looks like that. Well, at least couldn't you say that x bar was 0? So you're more likely only to be able to get 1 out of the 3 for free, but it's worth it because it's 5 minutes less work. You got one getting at? Right. I mean, if the shape's over here, as long as it's got a symmetry to it, you can at least get x bar. Right. So if the density function is symmetric, look at the region, and if you can find any axis of symmetry, vertical or horizontal only, then that gets you an x bar or a y bar. And that is us coming to the end. I'm going to see, although I have 2 more Zoom classes, if I can put together a couple of more examples of some homework questions for you. And anytime, tomorrow's going to be weird. I'm meant to be doing an in-service day tomorrow, but seems I'm the only one that's going. So you can certainly shoot me emails, and if I'm free, I'll answer them. But if I don't, I'll definitely get them answered by Saturday for you. If you have any other issues, feel free to shoot emails today because I will be available.
Oh, I have a quick question.
Yes.
The one where you change the y and z to polar, you put the
Yes.
x on the inside. Could the x go on the outside if it was independent of the y?
If it's numbers, yeah. If the integrals are numbers, you can shuffle them. The number ones, you can shuffle them. The variable ones, you can't really move them around too much, which is why I had to scribble out the first version, because the integral had a y in it. That then influences the values that you use as your integral in the second, which then has a knock-on effect to the third. But if the first and second, I'm doing it with my hands. If this is a number, and that is a number, and this isn't, right, and you're doing dy, dx, dz, or whatever, these 2 guys can be switched. That's okay. Right? But you can't pick this guy and stick him in the middle. Or pick, and definitely don't pick this guy and stick him on the end. That won't work. All right?
Okay, thank you.
So that was you were asking, yes?
Yeah.
Sometimes, yeah, because sometimes I answer not the question that you're asking, but the question I think you're asking, which isn't always the same thing. Okay, well, that's it. Anybody wants to ask me some things on a one-to-one basis, then just hang about while everybody else leaves, and I'll wait until the last one has gone and call it good. And have a nice weekend, everyone. Keep slogging away. Bye.
Thanks. Bye.
You're welcome.
Have a good day.
You too. Sarai, have you got a question for me, or are you just a little bit slow in leaving? Hi, Sarai. You still here? Okay.